Hi everyone, my name is Ben Oler. I'm Director of Marketing at Oxford Instruments Asylum Research. Thanks for making time to join us for our webinar today. Asylum President and Co-founder Dr. Roger Pruksch and Cypher Project Manager Dr. Mario Viani are going to be talking about recent advances in AFM technology here at Asylum. These advances have culminated in the Cypher, an AFM truly with no equal in the world. I encourage you to ask questions. You'll find a chat box in the webinar interface where you can submit those at any point during the presentation. We'll answer as many of them as we can at the end. If we run out of time, we'll be sure to get back to you individually. Also note that today's webinar will be recorded and available for viewing later. Simply follow the same link that you were sent in the registration email. We'll also send a follow-up email with that link and additional links to content that Roger and Mario will be presenting today. So with that, I'm happy to turn things over to Roger.
I'm going to start this webinar with a little look back in time. This photograph is actually from when I was a graduate student. I've spent many, many hours in this particular lab, although the guy in the forefront there wasn't there when I was there. And the idea here is that historically, if you look back, many AFM experiments have been pretty challenging. And a lot of times that was because you're trying to push the limits of technology, but even in many cases for even more routine measurements, it was because the hardware and the software was quite clumsy, wasn't very easy to use, was maybe very challenging to navigate. One of our primary design goals with the Cypher family and with our other instruments has been to design instruments and software that allow everyone to make what historically we might consider hero experiments. We've done this in a number of different ways by pushing the limits of what AFMs can physically measure and do as far as low noise, insensitivity to drift, and so on, and also by making the routine measurements and setup for those measurements more automated and simple to perform. We believe that the Cypher AFM embodies this design goal more so than any other AFM out there on the market today. So with this idea of the hero experiment, we're going to try to tell you today how everyone can be a hero. Now, one of the things that starts with is ease of use, and ease of use features that are kind of new here. I'm going to talk a little bit about GetReal, and then a new thing called GetStarted, which you may or may not have heard about on the Cypher, or I'm sorry, on the Infinity AFM. It's now available for Cypher. Mario Viani is going to tell us a little bit about some of the hardware and software things inside the development of Cypher that makes it really different from other AFMs. And then he's going to spend a lot of time looking at some really cool examples where we look at environmental control and so on with the Cypher ES, and blueDrive as well that enables that. After he's done, I will bounce back to some nanomechanical measurements. And really the nanomechanical measurements here are designed to show you that Cypher is a full-featured AFM, because one of the things you don't want to have to do is to swap heads, swap scanners, and do other things to make different kinds of measurements. So maybe you want to measure stiffness, maybe you want to measure electrical currents, and so on, with all while scanning fast, for example. Cypher enables those kinds of multimodal measurements. We released GetReal about a year ago, last August. GetReal is an automatic probe calibration routine, and the idea is pretty simple. Basically, with a cantilever probe, there's two unknowns. One is the stiffness, and one is the optical lever sensitivity, how far it moves for a given voltage deflection that you measure. So what we do with those two unknowns is we make two measurements. First, we make a thermal noise spring constant calibration measurement. Then we make a Sater method spring constant calibration. We use the results from both of those to solve for those two unknowns. And what we get out of that is we get the sensitivity and the stiffness of the probe. Now, this measurement is very simple. You basically choose your probe, and then you press a button, and everything happens automatically after that. This graph here shows a comparison between conventional force curve calibration sensitivities and GetReal calibrated sensitivities, and you can see that those values agree very well, and certainly within the standard sort of 5 to 10% uncertainty for these kinds of measurements. A nice thing about this technique is that it's safe. It protects the tip from touching the surface. You don't have to touch the surface to measure that force curve, and so your tip is nice and clean and pristine throughout the whole thing for when you begin your measurements. This feature is also free. It's for all our new and existing Asylum AFMs. We released GetReal about a year ago, as I mentioned before. And then a few months ago, we released something called GetStarted for the Infinity AFM. Now we're making GetStarted available on Cypher systems. What is GetStarted? GetStarted is basically a simple automated tapping mode imaging optimization routine where with just a few clicks of the button, you can get really beautiful tapping mode results. What is the idea? Well, it's pretty simple, actually. If you think about an AFM, one of the hardest things about running an AFM is picking the gains for the various feedback loops. And one of the things that's hard about picking the right gains is that the gain depends on the sensitivity of the various inputs, in particular for the cantilever and then for the actuators and so on. When we manufacture our AFMs, we already know the sensitivities of the piezo actuators, the closed-loop sensors, and so on. The cantilever really is the last piece of that puzzle. And as you might already guess, GetReal gives us that sensitivity. And so we can use that to automatically pick the gains. Okay, now you know a little bit about the idea behind GetStarted. The question is, how is it implemented? It's very simple. At the top of the master panel, click on the Get Started button right there. And then that will bring up a panel with a few things you can enter, so the scan size you'd like, the number of points and lines you like, and give us an estimate of the sample roughness. From that, you tell us the probe, you focus on the probe with the optics, you focus on the sample with the optics, and then you line the laser up on the cantilever with the spot-on laser, automatic motorized laser alignment. Once you've done all that, those little indicator lights turn green, and you sit back and wait for just a few seconds, and out will come some beautiful images. It's a really easy way to get started. That's why we called it that with AC mode imaging. This is really simple, and this is quite a realization for us because it's what some of our competitors said basically was impossible, that tapping mode or AC mode in air could be automated. We think you're going to find it very simple and very pleasurable to use. It's safe. The parameters, the gains, and so on are optimized before the scan starts. That means from the very first touch of your tip on the sample, the probe gains have been optimized, so you're much less likely to damage the tip than with methods that optimize it after you're already scanning. This feature is free on Infinity and Cypher systems now. We think that new users will use this to get started very quickly and efficiently. That's why we called it that. And even experienced users will really find that it's very, very good for their productivity. If you think this is interesting, we will be announcing an open beta testing period for Cypher customers a little bit later this year. Okay, now Mario Viani, the project manager for the Cypher family, is going to dig in a little deeper into some of the hardware and other features, as well as show you some pretty spectacular results. Mario?
Thanks, Roger. So I'm going to be talking about the Cypher AFM. The name Cypher actually refers to a family of AFMs, which right now is comprised of exactly two members. We have the Cypher S and the Cypher ES. The Cypher S was the first to come to market, and it quickly demonstrated high performance in terms of speed and resolution. More recently, we began shipping the Cypher ES, which added on environmental control, such as heating, cooling, perfusion of liquids and gas, all while still maintaining the bandwidth and performance of the Cypher S. In later slides, I'm going to describe the differences between the S and the ES in greater details, but first I'm going to show you some of the design principles behind the Cypher. This photograph dates back to 2006 and shows one of the original prototypes of the Cypher scanner. So one of the things that we learned from this prototype became an integral part of the design that we use today. Namely, that it's very important to make the mechanical loop between the sample and cantilever as short and high frequency as possible. In this image, the sample is here. It's a piece of mica. And the cantilever, though not visible, would be attached to the bottom of this block of metal. And so you can see that we have this very short and tight mechanical path between the cantilever and the sample. And this has a lot of ramifications for the instrument performance, both in terms of immunity to noise, such as vibration noise or acoustic noise, but also in terms of the drift performance of the AFM. One of the very novel things about this design, and you will not see this in any other AFM, is that the optical lever detection is completely decoupled from the cantilever holder. The optical lever detection is sitting up here above the scanner, but there is no direct mechanical connection between the cantilever holder and that detection system. By keeping the detection decoupled, we're basically able to keep the resonant frequency between the cantilever holder and the sample much higher than on any other AFM, because the mass of that detection system is not part of the equation. So here you can see the full Cypher prototype. The scanner is down here, and the optical lever is floating above the scanner. The Cypher scanner that ships today obviously looks much cleaner and nicer than the prototype I just showed you, but it still employs many of the same critical design features. In this slide, we have some images of the side view of the scanner and top view of the scanner, and perhaps most usefully, this perspective view here, which shows us a cantilever holder to which mounted is a cantilever, and it's perched a couple millimeters above the scanning stage, which has a grating magnetically held down to it. So this scanning stage scans in the X and Y directions 30 microns, and in the Z-axis it scans approximately 6 microns. This stage is able to achieve point defect atomic resolution, which is something that I will show you in a couple of slides. And it's important to note that that rigid, short, compact mechanical loop here between the sample and the cantilever is still intact. Another important part of the Cypher design is its ability to use smaller cantilevers. This is a topic that has been covered in great detail in the webinar listed at the bottom of the page. But for the purposes of this presentation, the take-home message is that small cantilevers are faster and quieter than conventionally sized levers. These optical images show 3 cantilevers that differ greatly in size. The longest cantilever is 200 microns, while the shortest is just 10 microns. However, the spring constants of all 3 levers are all approximately the same, about 4 newtons per meter. So if we look at the amplitude spectral density, which is just the square root of the power spectral density of the Brownian motion of these 3 levers, all immersed in water, we get very different resonant frequencies. The shortest cantilever has a resonant frequency of about 1 megahertz, and that is roughly 20 times higher than the resonant frequency of the 200 micron long cantilever. Now, since the quality factor of these 2 cantilevers are basically the same, this means that the short cantilever has an imaging bandwidth that is roughly 20 times faster. The other important thing that we can see from the Brownian motion is the magnitude of the force noise. So the force noise for the large cantilever is around 10 piconewtons, while for the small cantilever, it's about 2.5 piconewtons. And this turns out to be a very important factor for some of the measurements I'm going to show you in future slides. The final design feature that I want to discuss is the drive mechanism for the cantilever. During AC operation or tapping mode, the cantilever is excited to oscillate at or near its resonant frequency. Now, as most of you know, this is done using a piezo. The problem with this approach is the piezo excites the cantilever, but it also excites the support structure, or if you're working in fluid, it can excite the fluid as well. This means the driven cantilever response is a convolution of the drive response, which has the included structure from the support and the fluid, and the cantilever response. So you end up with this forest of peaks here, as was referred to in this paper by Tillman Schaper in 1996. Now, it turns out this forest of peaks is time dependent, and this causes a whole host of problems while imaging because your cantilever amplitude does not remain constant. On Cypher, we have an option that allows you to directly drive the cantilever and hence avoid the forest of peaks. It's called blueDrive. The principle is quite simple. You still have an infrared laser for detecting the cantilever, but now we introduce a second blue laser that we shine at the base of the cantilever. By modulating the power of the second blue laser, we can induce oscillations of the cantilever via photothermal excitation. So blueDrive basically replaces the shake piezo, and the beauty is that it produces tunes in air and in water that match what you would theoretically expect. Furthermore, there is no time dependence in the coupling, and this is critical for some of the data that I'm now going to show you. For more information on blueDrive, please view the webinar listed here at the bottom of the page. So now I'm going to transition from talking about the design of Cypher to looking at the performance of Cypher. The first point about performance is that the resolution of Cypher is unmatched. Here we have two examples. This left pair of images are of calcite and water. They show two sequential scans on the same area of the sample. We have a down scan and an up scan, and in both scans we can clearly see a single atomic point defect. The right two images show DNA absorbed on mica in solution. Again, we have a down scan and an up scan, and we can clearly resolve the DNA helix. We expect the periodicity of the the helix rather, to be around 3.4 nanometers. And so if I use this 10 nanometer scale bar as a reference, I see that I have three pairs of grooves. 1, 2, 3. And this may mean that we are resolving the major and minor grooves. I should note that both of these images were taken in AC mode with extremely small amplitudes, less than 1 nanometer free amplitude. Although people can routinely image with lattice resolution in contact mode, this small amplitude AC mode imaging is the only real way to resolve point defects. It is important to understand that this high-resolution performance with the Cypher is not difficult. We routinely demonstrate point defect resolution in demos and in customer labs. This collage here is a collection of high-resolution images showing either atomic point defects or the DNA helix. There are a few different imaging modes used to obtain these images, but all the data shown here is height data as opposed to error signal data. So I'll just point out a few of the images. These two images down here were taken in a demo for a customer who wanted to see frequency modulated AFM or FM AFM on calcite. Again, we see repeated defects in both the up and down scans. This image here was also taken in a demo. The customer was interested in seeing rubidium chloride solution, or rather seeing mica in a rubidium chloride solution. And you can see some higher features here overlaying the mica lattice. Presumably they are caused by the rubidium absorbing to the mica. And finally, this movie we have here was taken as part of the testing process for one of our production ciphers. We checked that every system is capable of atomic point defect resolution, and this series of calcite images was captured as part of that testing process. As you can see, there appears to be a little bit of drift, but keep in mind that the scan size here is just 15 nanometers, and the movie is showing 12 minutes of continuous imaging. Again, you can see in the movie repeated defects in the lattice. An important point that needs to be made in regards to the images that I've just shown you, lattice resolution is not the same thing as point resolution. You need to have a sharp tip to be able to resolve individual defects. This cartoon shows a relatively blunt tip, and it's not able to image this point defect or point vacancy. It cannot get down in there to image it. One of the ways you can see a tip is blunt is just to look at the step edge. A blunt tip will show a very broad edge with multiple steps, as seen in this image and as illustrated in this cartoon. A sharp tip, on the other hand, is able to get down and image those point defects and will show a sharp step edge. Getting point defects is not just a matter of being lucky and getting that perfect tip. It is also a matter of having an instrument that is able to keep that tip sharp after engaging in imaging. For that, you need an AFM that is low noise, has high imaging bandwidths, and it is using an imaging mode that does not expose the tip to forces so high that it causes the tip to break. I'm going to show you now how the Cypher performs in what might be called an unfriendly environment. That is inside a running Glovebox. This image here shows single atomic point defects on calcite where the Cypher was inside the Glovebox. And half of the image was taken with the pumps off, and the other half of the image was taken with the pumps on. This line here shows where that transition happened, but as you can see, it's difficult to tell which half of the image actually had the pumps on. Now this bottom image here is a simultaneous recording of the output of an accelerometer that was recording the vibrations of the Glovebox. And here we can see that the pumps were actually running for the bottom half of the image. However, in the topography image, we see no noise, and you can still see point defects. I should also point out that there was no vibration isolation used for this measurement, or for that matter, any other data being shown in this presentation. Cypher is not only a high-resolution AFM, it is also a fast-scanning AFM. We can see a few examples here. The webinar is not really all that good at streaming large areas of the screen, so I have kept the movies intentionally small. You can see these movies and others at their full resolution in our Cypher fast scanning gallery. The link here is at the bottom of the page. The important point here is that imaging faster is routine. This collection of videos was taken in both air and liquids. These DNA movies were taken in liquid. And the line rates were anywhere from 20 lines per second up to 160 lines per second. They were all taken with small cantilevers that had resonant frequencies anywhere between 3 and 5 megahertz. So the previous slide showed movies of relatively small scans on the order of microns taken with very high scan line rates. You can also use the speed of Cypher to generate very high pixel density images at relatively large scan sizes. This is a 30 micron image. It is a phase image taken of syntactic polypropylene polystyrene blend that was spin cast on silicon. This image was actually taken with a Cypher ES, and the sample is being held at 80 degrees Celsius. But the main point here really is the pixel density. This is a 6,000 point by 6,000 line image. And so I can zoom in by factors of 2, which I'm going to do now. And when I do that, you see I still have very high resolution. And one last time. Now we are zoomed in 16 times from the original image. You can see more images like this in our megapixel image gallery if you go to our website. Okay, so far I've been talking about the performance and showing data from both the Cypher S and the Cypher ES. Now I'm going to transition to talking just about the Cypher ES and the types of experiments that can be done under environmental control. The main difference between the Cypher S and Cypher ES can be seen in these pictures of the scanner. So at the top we have the side view of the Cypher S and the side view of the Cypher ES. And then we can look top down on the Cypher S and the Cypher ES. As you saw in an earlier slide, and you can see here, the Cypher S has a very open geometry. We have the cantilever and the sample, and it's exposed. On the Cypher ES, it's a little bit more difficult to see what's going on. You can see the cantilever here and the sample there, but you're actually looking through a glass window. And when you look from the side, you're actually looking through a glass chamber as well. If we zoom in a little bit, you can see it a little bit more clearly. There's the cantilever just a millimeter or so above a sample, and we are looking through a glass cell that's been backlit. Here's a cross-section of the ES cell in which you can see the main components. The cantilever is here, and although there is no sample shown, it would be magnetically attached here. Now the way this works is that during scanning, the diaphragm allows the XYZ sample scanner to scan the sample underneath the stationary cantilever. The diaphragm is highly flexible, and this means that you do not get the scanning distortion that is common with other AFMs that employ an O-ring to make this seal. But the diaphragm also ensures that we have a robust method for sealing the cell. In fact, the cell can maintain positive pressures up to 300 millibar. Now, if I expand the cell, you can see a little bit more about the construction. There are actually three components here, the cantilever holder, and then these bottom two components are the sample stage. The sample stage has electrical feed-throughs for making electrical measurements, as well as a port for perfusing in gas. There's also integrated temperature control, which allows you to heat and or cool the sample. Now, we have used just three materials to form the interior of the cell: fused silica, FFKM, which is a perfluoroelastomer, and stainless steel. Or alternatively, you can replace the stainless steel with PEEK. This means that the cell has an extremely wide chemical compatibility, allowing for a very wide range of chemicals to be introduced. The cell is also able to handle liquid perfusion. In this cross-section, we are exchanging fluid via two syringes. One syringe is used to push a little liquid into the drop, while the other is used to pull a little out of the drop. The nice thing about running in a drop like this is that it makes the cleaning of the cell rather trivial. This is because the liquid only comes in contact with your sample, which presumably you have control over, and the cantilever holder, which is constructed out of fused silica and can be fully immersed in a cleaning beaker. It's not actually necessary to use syringes. You can also use gravity flow to push fluid through the cell. Because the cell is sealed, the fluid will stay in a drop in a gravity flow situation, even when using something that has lower surface tension, like isopropyl alcohol. Here's an example of an experiment where we use gravity flow to perfuse solution into the cell. So here we have a piece of calcite, which is the most stable polymorph of calcium carbonate. It's a crystal that's easily cleavable, and so we cleave it and we take it, we put it into our closed cell. It's not shown here, but imagine it sitting right here underneath the cantilever. And then we add a drop of growth solution. So now if you use the Cypher to hunt around for a little bit, and if you're a little bit lucky, actually this is a case where fast scanning is really a big help, because if you're looking over large areas to find a screw dislocation, you can do that much faster with the Cypher. So if we look around for a little while, we can find a screw dislocation like shown here. Here's a schematic of, or a cartoon of what a screw dislocation looks like. You see as we walk around the screw dislocation here, we're actually crossing a single atomic step, and this is 0.3 nanometers high. Now, if you flow a solution of calcium carbonate over the calcite, you begin to observe the calcite grow, and now you can see the movie playing. This is elapsed minutes and seconds here. So these images were all taken under continuous flow. We are not the best chemists in the world, so we did not know the exact pH we needed to change from a growth to etch solution. So you can see some changes in the growth rate. And at some point here, we get it right, and we see that the calcite surface begins to etch. And then we reintroduce the growth rate. You think that the screw dislocation may have disappeared, but in fact, that's not possible. And when we start the growth again, you can see the reemergence of the screw dislocation. And here the movie has started playing over again. So you can see this movie in full resolution again in our Cypher fast scanning gallery, and the link is here at the bottom of the page. For those of you with a lower bandwidth connection, this slide shows some of the frames from the movie. Note that the images are in order, but I was not able to space them equally in time and show the whole process. So the top row of 5 images is at the beginning of the movie, and it shows calcite growth. Those frames are spaced by 6 seconds. Then we start etching in this middle row of 5 images, and here each frame is spaced by 40 seconds. And then finally we start growing again, and that's shown here in the bottom row of 5 images. And we can see so the frames here are spaced by about a minute, and we can see the re-emergence of the screw dislocation here in the last frame. So one of the historical and semi-common problems with performing measurements in liquids on an AFM is the potential for a leak. And a leak with a buffer solution or salt solution can be a very expensive repair, or lead to a very expensive repair. So one of the things that we did with the Cypher ES is integrate a pressure sensor right into the system. So this means that you can test for leaks in the cell before you ever add any fluid. The idea is rather simple. You basically take a syringe and you pump a little air into the cell. And then you wait and watch on your computer screen to see what happens to the pressure. The pressure should go up, and it should stay relatively constant if you do not have a leak. If you see any drop in pressure, then you know that something's wrong, and you better check things out before you add any liquid. So I'm going to show a movie now of the process. Here we see 2 gas lines going into the cell, and these lines come underneath this cover, which is held on magnetically. And one of the lines goes to a plug, so it's just stopped, and the other line goes to a syringe, which right now is outside of the field of view. And that's the syringe that we're going to use to pressurize the chamber. And after we do that, then we will watch this graph here, which is going to give a live update of the pressure inside the cell. So we start the movie. Open the valve that allows me to push air into the cell, so the pressure goes up. When I'm done pressurizing it, I close the valve, and then I can take the syringe off, and now I just watch the pressure. It relaxes a little bit in the very beginning because of the flexible diaphragm that forms part of the cell. But then we fast forward in time, open it up, the pressure drops. We see that we had a airtight seal, which means that it is safe to add liquids to this cell. Okay, so I've showed you an example for perfusing liquid through the cell. There's other experiments that you can do, such as heating and temperature control. And it turns out that the way you change from one type of cell to another is rather easy. You just pull it out. There's a screw in here that clamps in this dovetail. And so here we're dropping in a heater sample stage. You see there's a electrical connection, a cable that comes out of the side of it. This particular cell will go from ambient to 250 degrees Celsius. It's ceramic and fused silica is the construction of the actual heater. This means it has very low thermal drift, and we're able to make movies over quite large temperature ranges without removing the tip or disengaging from the sample. So I'm going to show some examples of that. Here is an example where we use the Cypher ES to ramp the temperature of a sample. In this data set, we ramp the temperature from 60 degrees C up to 140 and then back down to 60 degrees C. And we continuously image the whole time to make a movie of what is happening. Now, the duration of this experiment is approximately 4 hours. The sample here is a blend of syntactic polypropylene and polystyrene that has been spin cast onto a silicon substrate. And the images that we are showing are the phase images. They show the highest contrast between the syntactic polypropylene and the polystyrene. Now, these islands here are the polystyrene, while everything else in between is the syntactic polypropylene. In a second, I'm going to start the movie, but first I'm going to walk you through what happens. The first frame of the movie shows the sample when it is about 60 degrees C. Now, as I heat the sample to 113 and then 135, we see that these little crystallites here, they begin to melt. And in fact, when I play the movie, you will see some of these smaller crystallites up at 135 degrees, they start to dance around as they are floating on this pool of melted polypropylene. Now, as we cool the sample, the crystals act as nucleation sites and then grow into larger structures. And finally, when the sample cools down to 60 degrees C, which is the original temperature that we started at, we begin to see a different phase of the polypropylene solidify in between the crystallites. Okay, so now I'm going to start the movie. The graph here is showing the temperature as a function of time. And so we're just getting to 100 degrees C now. And the little crystallites are melting. And you can see some of them dancing around now. And as we cool down, the crystallites start to grow. So one of the important things to point out about this experiment is that it involved ramping the temperature over an 80-degree range. And yet we were able to image continuously over the same region of the sample. I realize there's a lot going on there. If you would like to see it again, please see our website. And as a lead-in to the next movie, note that we took this temperature to about 140, where there was still a fairly high density of crystallites. If we heat the sample until the crystallites are mostly melted, we get a very different movie. So I'm going to show that to you now. So for this movie, we are going to look at just the cooling cycle. Note that the starting temperature of this movie is about 140 degrees C, but most of the crystallites you can see are gone because they have melted. So now we see something very different as we begin to cool. Okay, so here I'm going to start the movie. And I'll just pause it here for a second. It appears that there was a crystallite, maybe out of our field of view, perhaps over here, that recrystallized and came into our field of view. So now I'm going to continue the movie. And continuing on, we get a very different morphology compared to the structure we saw in the previous movie. I've just shown you two examples of temperature control. These experiments are easy to perform, and part of the reason they are easy is that the hardware was designed from the ground up with temperature control in mind. So for many of our competitors, environmental control was really an afterthought in the design, and you can see this with the addition of boxes of electronics and pumps and cables, etc. The image here is actually from the user manual of one of our competitors' microscopes, and you can see all the additional hardware that's required to run at non-ambient temperatures. The beauty of the Cypher design is that the heating and cooling experiments really need no additional hardware. If I were to show you a picture of the additional hardware, this would be replaced by nothing. It would be an empty space. So this basically means to image at temperature with a Cypher, you really need to do just three things. You mount your sample on cantilever, you enter your temperature and or ramp rate into the software, and then you engage an image. There's no messing with all of this. I should point out that this is not just a matter of ease of use. This is also a matter of performance. When you add pumps, then you run the risk of adding additional noise to your images. If you look at the picture here, you can see they have something called a pulse damper, which I don't know exactly what that is, but I presume it is used to reduce the effects of pump noise making it to the scanner through the cooling lines. The last example of environmental control that I want to show is of the solvent annealing of a block copolymer. In this case, we have a polystyrene, polybutadiene, polystyrene block copolymer that has been spin cast onto silicon. Now, these block copolymers are known to organize into various microphase morphologies, but the morphology of the spin cast sample might not be its lowest energy state. So as we expose the toluene, as we expose the sample to the toluene vapor, the polymer swells a little bit and is able to reorganize. So here I've made a movie of that process. The movie starts right as I start to perfuse the toluene vapor through the closed cell. This is a 4-micron scan with 1024 pixels by 512 lines. So I will play the movie at the full field of view and then again zoomed in so you can see more detail and what's happening to the morphology. Note that the duration of this experiment was just over an hour. Okay, so I'm going to start the movie now. And you will see some delamination at the very end of this movie. And now we're going to look at it again, but zoomed in. And we'll take snapshots of this area at time equals 0. Time equals 18 minutes. Time equals 32 minutes. And finally at the end of the movie at 63 minutes. And if I pause the movie for just a second, you can look at the two highlighted regions and see some significant changes in the morphology. Okay, now we're going to continue on and just look at one of those areas and play the movie forwards and backwards. And you can see the changes happening in real time. I realize that some of you may not have been able to see that very well depending on the bandwidth of your connection, so please take a look at the link at the bottom of our page and you can replay that movie at your leisure.
Thanks, Mario. We mentioned in the beginning that Cypher is a full-featured microscope. You don't need to choose between environmental controls and fast scanning with current measurements like STM and Orca and so on. Another example of that are nanomechanics. So things like fast force mapping mode where we look at higher speed force curves, AM/FM viscoelastic mapping, contact resonance, force microscopy. These are all examples of things you can do with environmental control at fast scanning and fast scan rates and everything else. I should also mention that these nanomechanical methods, there's a lot that are listed in our Nanomech Pro toolbox, which I'm not going to go into detail here just because of lack of time. I should also mention that we have resources where you can learn about these at these websites, or at the webinars that we have down here that have already been given out. Since we don't have a ton of time, I'm going to concentrate on an area where there seems to be a lot of interest, and that is in nanomechanics. I'll talk a little bit about fast force mapping. I'll talk about some new results in AFM viscoelastic mapping, and I'll finish up with contact resonance measurements that we've made. In particular, although you can do these things without blueDrive, it turns out that for some of the experiments, especially some of the things Mario showed you, because of the stability and ease of use of blueDrive, they tend to be easier and work a little bit better. I showed this slide in a previous nanomechanical presentation. What it shows here is measurement time, so ranging from, say, if you have a 10 Hertz line scan rate for a 256 by 256 pixel image, it will take you about 25 seconds. As you go slower, so down to maybe 1 Hertz per pixel, or 1 millisecond per pixel, that gives you a 1 Hertz line scan rate, and it'll take you about 4 minutes. And so on and so forth, all the way down to if it takes you about a second per pixel to do a 256 by 256 image will take you on the order of 3 days. Now if we look on the horizontal axis, this is the modulus range covered by the various techniques. So we have nano indentation, which is a pretty wide range, conventional force curves, which are one of the oldest and sort of most venerable and very useful nanomechanical measurement techniques. If you speed those up, we have fast force mapping, which I'll talk about on the next slide a little bit. Then techniques like force modulation, contact resonance, which I'm going to talk about, and then our new AFM viscoelastic mode, which is basically based around an AC technique tapping mode. Fast force mapping mode is a fast force curve technique where we oscillate the base of the cantilever or the sample in the case of Cypher, in the case of the Infinity AFM up to 300 Hertz, and on the Cypher S and Cypher ES up to 1 kilohertz. Now that greatly speeds up the acquisition of force curves. Here's some examples here. This is on the polystyrene polycaprolactone sample, and you can see the force curve on the polystyrene here and the polycaprolactone here, both having a different slope and different amounts of dissipation on this. Now this image right here just shows the topography with the modulus extracted from a simple Hertz model pasted on top or colored on top of that. This technique takes a few minutes, and depending on the resolution, maybe up to tens of minutes for these high-resolution mechanical property maps. What we do, which differentiates us from others in this, is that we capture the entire force curve at each pixel. So everything is completely captured for the entire image. And what that means is that afterwards, if you have questions or other ideas, you can go and fit that data. Also, we capture this at 1 kilohertz, and we don't throw away any force curve. So there's not one that we measure for measuring the topography and then throw away and then capture one for the mechanics. We actually capture all of that, and so you can see exactly what the tip has done throughout the whole process. And again, as I showed on that previous slide, this covers a pretty large modulus range. I should outline, though, that to cover this modulus range requires you use a range of cantilevers. Any given cantilever is probably going to be good for a couple orders of magnitude in modulus, not much more than that. So how does this work? It's really similar to a very old technique in AFM called jumping mode. or pulse force mode. Basically, the tip is moving up and down with the sinusoidal trajectory. We scan continuously over the surface, and the maximum force is the feedback variable. So the set point is basically the maximum force you want. We typically collect two channels, the deflection and the Z sensor, everywhere. And the Z sensor is very important because if you don't know what the base of that cantilever is doing, it makes it very hard to later fit that to anything quantitative. And we can display live channels, so Z sensor, adhesion, max force, air channel, and the modulus. And then in addition to that, post-processing, you can display any number of channels. So you can look at different kinds of moduli calculated from different models, adhesion calculated from different models, and so on and so forth. Okay, I'm going to move on to AM/FM viscoelasticity mapping. Again, this has been covered in previous webinars. Just briefly to introduce it again, it's a tapping mode technique. That's where the AM comes, the amplitude modulation. Tapping mode means that we're using the first resonant mode amplitude as a feedback signal to control the tip sample distance. At the same time, we excite a higher resonance in the cantilever, and we actually phase lock that so that we have a frequency modulated channel there. This combination of the higher mode frequency shift and the lower mode phase shifts gives us both elastic and viscous information about the tip sample interactions. So we can, in the earlier webinar, we discussed this AM/FM technique. What's happened since then is there's actually been a decent amount of work in this area, and especially in the theoretical front. And what's happened is we've been able to actually take, for example, different models, and for example, the Hertz model. Hertz model for a punch is linear in the indentation. So this is the elasticity. This is the force between the tip and the sample. Elasticity, tip radius, and the indentation. You can look at that same model or similar model for a sphere. There's an elasticity, radius, and then now the indentation. That's a nonlinear indentation. And finally, for a cone, our SNED model, we have the elasticity. We also have a cone opening angle, and we have the indentation depth, which is now squared. Recently, as I mentioned, there's been a lot of work on converting these in AC mode, especially bimodal mode, to basically something that's like a Hooke's law, where we convert the frequency shift and the phase shifts into a measurement of the modulus in the indentation depth. I'm not going to go into depth that. You can read these papers, but basically it turns into some math that you can put into a real-time or offline calculation where you choose the model, in this case a sphere, and you choose the radius, in this case 10 nanometers, and you convert that into the amplitude, phase, and frequency measurements into a modulus map, and at the same time into an indentation map. Now this is kind of an interesting sample, just to note here. This is actually a pretty stiff sample. It's a solder. And so we have topography here, and painted on top of the topography are the modulus. And you can see very clearly in this, there's actually 3 phases separated, starting somewhere down around 30 up to maybe 45, 50, and up to above 50 gigapascal. At the same time, you can see that the indentation depth in this map here is, as you might expect, the stiffer materials have a slightly smaller indentation, so something below a nanometer. The very soft stuff, purple here and with higher yellow indentation here, goes up to a whole 1.05 nanometers or so. If you want to read a little bit more about these kinds of samples, it's right here. But what's exciting about this, well, there's a lot of things that are exciting about this. What's exciting to me is that we actually now have a very robust and easy estimate of these material properties, the modulus, and the indentation depth. They're self-consistent. And also you should note that these materials are rather stiff. This was measured with an AC 160 cantilever, relatively stiff materials. In the next couple slides, I'll show you the whole range of that. Okay, for high-speed AM/FM modulus mapping, we're going to look at an Aero UHF lever. A lever like that is pictured right here. It has a quality factor of about 100 and a resonant frequency of about 1.5 megahertz. We can do a back-of-the-envelope calculation of the time per pixel for that, and that's going to be related to the quality factor and the resonance frequency. If we plug those numbers into this and multiply by the number of pixels in a line, we get to a line scan rate estimate of about 15 hertz. Now, I should note that the speed limit for AM/FM is limited by a couple things. The first is that in the first resonance, it's typically the quality factor of that resonance. Or if it's the second resonance, it's the frequency of that. If we have a second mode resonance that's well above our detector bandwidth, it's hard to use that. So let's see what we can do with this Aero UHF. First of all, sort of as a baseline, we'll just measure at 1 hertz. This image took 256 seconds to complete. You can see here there's a grayscale with that's in gigapascals, so we're making a quantitative measurement here. We can double that, virtually the same. If you look very carefully, you won't see many differences. We'll multiply that now by a factor of 10, so we'll go up to 20 hertz. And you see there's a few very, very subtle changes there, but it's almost the same. We've gone up by a full factor of 10, so this actually takes less than 13 seconds to complete. We can push it a little bit further. Now we're under 10 seconds. We've gone up to a line scan rate of 26 hertz. You can start to see a little bit of ripple there where that AC, or the Aero UHF, is starting to have a little bit of trouble at that step edge. If we push it all the way up to beyond the speed limit, we're breaking the law here. We're up at 78 hertz. This image takes 1.6 seconds, and you can see there's still contrast, but clearly not quite the same image quality as before. Okay, for the final 2 slides before we finish up, I want to tell you something we're actually fairly excited about here, and that is that we can apply blueDrive to these nanomechanical, especially the AC nanomechanical measurement modes. And as I mentioned before, it improves the stability, it improves the matching with models, and in fact it works so well that it works both in air, as you might expect, but also in liquid. And just here's one quick example of AM/FM viscoelasticity mapping. Modulus mapping, this is a polystyrene polycaprolactone sample, the same sample we looked at before, deposited on mica. Here is the modulus map in air, ranging from 0 to 4 gigapascal. And then this is the same sample, same cantilever, only in a liquid environment. And you can see here that the scale, the modulus scale, matches quite closely, and that those two things agree quite well. We haven't applied this to a large number of samples yet. It's still fairly early days, but it seems to work quite well on this nice test sample. The next and final example of blueDrive enabling nanomechanical measurements is with contact resonance force microscopy. Now, you may remember, if you've looked at the previous webinars, basically in contact resonance we bring a cantilever down in contact mode with the surface, and then we oscillate that. blueDrive oscillates the base of that cantilever and induces those resonances. Now in air, a piezo and a photothermal excitation give you more or less the same results, but in fluid it's a different world. So this red curve shows the piezoacoustic, and you can see there's basically no recognizable resonance curve there, whereas the blue shows you the photothermal drive, a nice, beautiful curve as we'd expect. If you want to read more about it, there's an archive reference up here with Marta's paper on it. So the 2 examples I'm going to show you that are here. One, this is a ternary blend, so this is polystyrene, polypropylene, and polyethylene. And I won't go in great detail on it, but this is in air, this is in water. Topography here, and the topography maps match. The resonant frequencies are here. The scales are different, but the contrast is similar. Here's the quality factor, and here's the elastic modulus that's calculated from that. These histograms at the bottom show you the modulus measurements for those 3 components, and the fit in air and water match within a few %, which is very nice. Now that's around 2 gigapascal. We can also go up again to the 100 to 160 gigapascal range. This is the same cantilever, again in contact mode. This is our silicon titanium sample. Now here's the topography in air and water. Resonant frequency shift. Again, the scales are different, but the contrast is similar. Quality factor. And then the elastic modulus. And again, if we look at the histograms of those two values, we get very, very good agreement. So this is actually exciting for us in that it actually is the first, well, not the first, but it's a very practical and very easy to implement and to operate contact resonance measurement in liquid environments.
Okay, thank you, Roger. Thank you, Mario. We ran a little bit long, but we'll go ahead and take some questions now. If you haven't submitted them yet, go ahead and type them into the interface. And if we don't manage to get to your question here live right now, we will get back to you individually. So Mario, we'll start off with you. There was a question, how does the XY drift on Cypher compare to the MFP 3D?
Yeah, so minimizing the drift in Cypher is one of the things we really worked quite hard on, and when we were designing the Cypher, and so it actually has much better performance. I would say the drift is down near 20 nanometers per degree C, and that per degree C is of changes in the lab temperature. And that's also with the addition of the air temperature controller, which is an option I didn't talk about, but it's a mechanism for keeping the temperature of the Cypher constant.
Okay, thanks, Mario. Roger, this next one might be best for you. What applications benefit most from operation in a Glovebox?
Thanks, Ben. Well, Gloveboxes are good for controlling oxygen and humidity levels and so on. So a few examples might be organic photovoltaic materials. A lot of people interested in battery materials make measurements inside of Gloveboxes, and also things like fuel cells. We've also started to make measurements inside Gloveboxes for just simple force measurements. Any place where maybe some surface water may play a role, it tends to help a lot.
Okay, thanks, Roger. Mario, for you, does blueDrive require any special cantilevers?
Yeah, this is one of the beauties of blueDrive. It will work on any lever. The caveat to that, though, is that you get the biggest amplitudes when the cantilevers are coated. So say if you have a gold coating or something like that, you will get the biggest amplitudes.
Okay, thanks, Mario. Roger, a question about fast force mapping. How is that different from other nanomechanical mapping modes that also use fast force curves?
That's a good question. And in part, I won't be able to answer it because some of the other fast force mapping modes out there, or fast force curve modes out there, we don't really know that much about. They're a bit of a black box, so there's some mysterious things that do happen. What I can say is that we capture every single force curve, and we do it, that our force curves are not open loop in the sense that we capture both the deflection and the Z sensor, so you actually know where the base and the tip is at every point in time. We don't do any sort of mysterious black box background subtraction. You see the force curves that we actually measure, sort of warts and all. So you can be confident that what you're seeing is actually what the cantilever is doing.
Okay, thanks, Roger. Mario, another for you. Do you use the same size laser spot for all cantilevers on the Cypher?
Yeah, it turns out that we actually have laser modules that allow you to change the size of the spot. And the reason that's important is that you actually want to match the size of the laser spot to the cantilever to get the best optical lever detection. It may not be obvious, but I believe this was covered in one of the earlier webinars in greater detail. Okay,
thanks, Mario. Roger, another question for you. is it necessary to acquire the AM/FM mode and contact resonance modes separately if I already have blueDrive?
Oh, that's a good question too. I guess I wasn't clear about that. No, blueDrive really is it's not a mode. It's a drive mechanism, and it works great with both AM/FM and with contact resonance. So if you have blueDrive, you'll be able to do both of those. You'll be able to run both of those measurement modes quite well.
Okay, thanks, Roger. We have run over a bit, so I think we might just call it here. Thank you all for attending. If we didn't get to your questions here live, we will get back to you here in the next day or two. Thanks so much for attending, and please keep an eye out for our future webinars. Thanks a lot.